This video is for the solutions of the review sheet for topic 6 and 10. So first, let's start with the multiple choice. Now, the first question wants us to compare. It's a ratio question, and we've learned to deal with these questions as making a table first for the two planets that are given, so let's do that. We know on planet X we have a gravitational field strength of 18 Newton per kilogram, and we're looking for the G on Y. What else do we know? We know they have the same density, and we know that the radius of Y is 3 times radius of X. So let's put an R here and a 3R here. Now, to write an expression for being able to compare these two, we need G, which gives GM over R squared. So we have their radius ratio, but we don't know their mass ratio. Well, we know mass is equal to density times volume. So let me write that here. Density is mass divided by the volume. So if they have the same density, their mass is proportional to their volume. And volume of a sphere is proportional to the cube of R. So the proportionality of R cube will be their proportion for mass. Since Y has a radius 3 times that of X, if the mass of X is 1m, cube of 3R would be 27R cubed, so 27 times more volume. To keep to the same density ratio, we have to have this mass is 27 times the mass of X. So if this equals 18, we're given that this expression is equal to 18. Let's write the same expression for Y. We have G, 27m, divided by its radius squared, which is 3r squared. This gives a factor of 9 in the denominator, so 27 over 9, that is actually 3 calculates to 3 gm over r squared. If each gm over r squared is 18, 3 times 18 will be 54. Question number 2. This was one of our review questions when we were learning this topic. So we're looking for the greatest work done by the gravitational field. So work done is either positive or negative. A positive number is always larger than a negative number. So we're looking for the positive work done by the gravitational force or field. That is when the movement is in the direction of the gravitational field. So we're looking for the answer that goes from the higher level to the lower level, because the gravitational field is attractive. So when we move in the direction of the field is doing positive work, and we're looking for the greatest one, so the positive one. Among the options, that would be C. It could have also said Q to S. It could also say Q to P, or R to P as stated here. It could also say R to S. All of those would be the correct answer if it was given like that. Number 3 is asking for the proportionality between f and the separation r as a linear function. Since we know f is proportional to 1 over r squared, plotting f divided by 1 over r squared would give a linear relationship. Number 4, now here is where we need the escape speed ratio. So we want the escape speed for a planet. We're comparing two masses again, the moon and the earth. So let's make our table here. Here would be the earth and here would be the moon. What do we know? We know the diameter of the moon is 4 times smaller. So if this is, well, if the diameter is 4 times smaller, radius is also 4 times smaller. So we know if this is 1r, we can write that as 4r. And the mass is 81 times smaller. So if this is m, this would be 81 m. So the escape speed is proportional to the square root of m over r. This is proportionality. I'm not worrying about the constants because these are what I need. So for Earth, I can write that as 81 over 4, 81m over 4r. For the moon, that would be m over 4r, but these are in square root. So if this is v, how many v would that be? Well, simplify 81 over 4 as 9 over 2 outside the radical. That would be 9 over 2 times square root m over r. Sorry, there shouldn't be a 4 here. That's my mistake, my bad. So that's, how many v would that be? If this, you rearrange, you would get this as 2 over 9 of the escape speed of Earth. Number 5, answer is C, because we discussed the higher orbit would obviously, since it's at a larger height, has larger gravitational potential energy, so we eliminate these two. And at a higher orbit, the kinetic energy would be less to maintain. The closer the orbit, the higher kinetic energy a satellite would have to maintain the circular motion, basically because you have a stronger force acting. So at y, at the higher orbit, you would have an increased potential energy, a larger potential energy, and less kinetic energy compared to orbit x. Number 6 is B, because you have a mass attached to a string rotating in a gravitational field. How do the tension in the string and the kinetic energy compare at P and Q? Now, the tension should be greater at Q. We know this from circular motion because tension must be larger than the mg to provide centripetal force, whereas it can even be 0 at the top point. So, well, here as well. But we know how to compare the top and the bottom, but now we're using that information to qualitatively compare P and Q. So we can still conclude that at P the tension can be less, because we know at the bottom it would be maximum, so we know it's greater at Q than P, which also means it has to be moving faster because the tension is larger. So you can also answer this from conservation of energy. Here, compared to this ground level, here it would only have kinetic energy. So that total would split into some kinetic energy as it goes from the top, but here it's also at a certain height. So that sum would be equal to that value at Q. Same for point P. So at any point, the kinetic energy would be less because the total kinetic at Q is shared between the kinetic and potential at any point at a higher location than Q. So answer is B. Number 7, we have 2 points X and Y. We know X is 2L. Sorry. We know X is 2L from the center, and we know Y is L from the center. So as they travel in their circular motion, the tangent velocity will be proportional to the radius. So because they have the same angular velocity. So if this is moving with linear v, this is moving with linear 2v. To compare acceleration, we can use v squared over r. For x, it's 2v squared divided by 2l. For y, it's v squared over r. When you rewrite this, it's 4v squared over 2l. Let's say that is an l. And that becomes 2v squared over l, because these two would simplify. And this is 1v squared over 2l. You can see the x acceleration is twice the y acceleration. Therefore, our answer is B. And the last multiple choice here, we have, again, a comparison with another planet for Earth and another planet. Let's make our little table. We have on Earth G, we're looking for G on the planet in terms of G. What do we want to know? Since G is constant times mass over r squared, we want to know their mass and radius comparison. We know they have the same density. Again, we're given the density. A planet has double the radius. So if Earth has r radius, this has 2r radius. Now, once again, we need to use the density to compare the masses of the two planets. Now, let me explain that again. Density is mass divided by the volume. You can rewrite this as mass equals density times the volume. So you can see that mass is directly proportional to the volume. The volume of a sphere would be 4/3 pi r cubed. You don't have to know that full thing, but it's given in the data booklet if you want. So just so you know that the volume of a cubic object, a three-dimensional object, will be proportional to the cube of the radius. So if this is 1r and the mass is m, cube of 2r ratio would mean this has 8 times more mass, which means you write the expression for the gravitational field strength on the planet. G, its mass is 8 times bigger, and its radius is 2 times bigger, which simplifies into 8/4 gm over r squared, which means 2 gm over r squared, so 2g.